This is pre-calculus section 2.2 on polynomial functions of higher degrees. So we're not just looking at linear functions or quadratics, we're looking at even higher exponents than that. And we're going to say two general things here. First of all, a polynomial function is continuous. That means we can draw the entire curve without having to take our pencil off the paper. And it cannot have any sharp turns. So as I look at number one, first of all, yes, it's continuous. I don't see any big turns. So letter A, yes, that is going to be a polynomial. Letter B, once again, it is continuous. That is great. There are not any sharp turns. All of them are rounded. So once again, polynomial, yes, it could represent a polynomial. Letter C, the first problem I see here is this big jump discontinuity. So letter C is a definite no. And letter D is continuous. However, we do have those sharp turns. We have linear on one side, linear on the other side. This is what it looks like to have a sharp turn, so this would not be a polynomial function. So what do different polynomials look like just in their most basic form as a parent function? X to the second, x to the fourth, x to the eighth. If we look at all of them on the same graph, the graph is going to look something kind of like this. There is y equals x squared, and comes y equals x to the fourth, and then lastly we're going to have y equals x to the eighth. All of them have the same general form to them. And I want you to notice the end behavior for all of them. As x goes towards infinity, f of x is going towards positive infinity or going up. Likewise, as x goes towards positive infinity, towards the right, f of x is going towards positive infinity as well. Next, let's look at y equals x cubed, and y equals x to the fifth. So another pair of graphs that all have odd exponents and their parent functions without any variations on them. So here are functions. Let's take a look at the graph. There's y equals x. The red is y equals x cubed, and the black is y equals x to the fifth. Unlike the even functions, the end behavior as x approaches negative infinity, f of x also approaches negative infinity. And as x approaches infinity, as x goes to the right, f of x approaches positive infinity. So for our odd functions, they're always going to be going in opposite directions of each other. And depending on our leading coefficient, in this case, our leading coefficient is positive. It went down on the left and up on the right. Whereas if our leading coefficient was negative, then our end behavior would be up on the left and down on the right. Next, let's look at y equals x cubed, and y equals x to the fifth. So another pair of graphs that all have odd exponents and their parent functions without any variations on them. So here are functions. Let's take a look at the graph. There's y equals x. The red is y equals x cubed, and the black is y equals x to the fifth. Unlike the even functions, the end behavior as x approaches negative infinity, f of x also approaches negative infinity. And as x approaches infinity, as x goes to the right, f of x approaches positive infinity. So for our odd functions, they're always going to be going in opposite directions of each other. And depending on our leading coefficient, in this case, our leading coefficient is positive. It went down on the left and up on the right. Whereas if our leading coefficient was negative, then our end behavior would be up on the left and down on the right. Here in a little more detail here, if n is odd, if the largest exponent is odd and our leading coefficient is positive, then as x goes towards the right, f of x goes towards positive infinity. As x goes towards negative infinity or to the left, f of x goes towards negative infinity. So with the end behavior, we're going to be looking at the function going in opposite directions. Keeping with that theme, if the leading coefficient is negative, then as x goes to the right, f of x goes down. And as x goes to the left towards a negative infinity, f of x goes up. We could have a lot of terms in there or very few terms in there, but the end behavior has to be consistent. Now looking at if our largest exponent is even, the degree of the polynomial is even, and our leading coefficient is positive, then as x goes to the right and to the left, f of x is going up towards infinity. So towards the left, towards the right, there could be a lot of terms in there, but we know that they're both going to be going up as they go off towards positive and negative infinity. If the leading coefficient is, you should say negative here, then as x goes towards infinity and negative infinity, f of x goes towards negative infinity, or in other words, it keeps going down in both directions. It goes down to the left and it goes down to the right, with potentially a lot of terms in there, or maybe just one term. Now, speaking of the terms, you're going to have a maximum of n minus 1 turns. So if our largest exponent is x to the 5th, you might have 4 turns, or 2 turns, or no turns. Whatever the maximum number of turns is, which would be, again, 1 less than the higher degree, you could have that many, or subtract 2, or subtract 4, or subtract 6 from that to figure out how many turns it actually has. As a couple of examples here, we're looking at n behavior. For the first one, I noticed that my largest exponent is odd. The leading coefficient is negative. So as x goes towards infinity, let's see, negative and odd means it's going to be doing something like this, maybe with a bunch of turns. But as x goes towards the right, f of x goes towards negative infinity. And as x goes to the left, f of x goes towards positive infinity. Second example, my largest exponent is even this time, and the coefficient on that is positive, which means to the left and to the right, it's going to be going up. It's x squared, so there's going to be 1 turn in there somewhere. So as x goes to the right, f of x goes towards positive infinity, and as x goes to the left, f of x goes towards positive infinity. Detail at these polynomials. So if you have a polynomial with degree n, and it's in standard form, so I have it listed first, then you have at most n real zeros. In other words, if you plug a value in for all of the x's and you evaluate it, you get a value of 0. And then you also have at most n minus 1 relative extrema. And that goes back to the turning points that I talked about earlier. So if we're looking at a graph of something, and I say, what do you know about this? Well, first of all, it has to be an odd function because the n behavior is going down to the left and up to the right. And I'm seeing 2 turns in there, so I think it might be x cubed. It could be an x to the 5th or x to the 7th. We'll talk about multiple roots here in a second. But because of the 2 turning points, we have a relative maximum and a relative minimum. So the number of relative extrema corresponds to the turning points. And as far as the terminology goes, we can talk about zeros, solutions, factors, and x-intercepts, and they're all going to be synonymous with each other in this context. So to look at an example over here, if I have f of x equals some polynomial, and I believe x equals a is a 0 or a root, that means I plug it in for all of the x values, and if we run it through the actual polynomial, the value comes out to 0. If I said f of x equals this, and I want to know where does this equal 0, then I could call that, say the x equals a is a solution to this function f of x equals 0. And if a is a 0 or a root or a solution of the polynomial, then I can factor it as x minus that a value. And as far as it applies to the graph, then a comma 0 would be an x-intercept of the graph. And we're going to look at an example of that here in a moment. If you do have a repeated 0, let's say that a number works more than once. If it's repeated 3 times or 5 times, it's going to pass right through the x-axis. Sometimes that's called a pass-through point. But if k has an even multiplicity, so if it's a double root, a quadruple root, we get what's called a bounce point, which will be giving us a local minimum or maximum. Okay, so let's look at this a little more detail with this problem. Find all the zeros in relative extrema. And we'll be looking at a lot of different ways to solve problems like this. But as I noticed right away, it's not x squared and x, but it's x to the 4th, x squared, and 1. I kind of recognize this pattern. It's going to factor as x squared minus 1 times x squared plus 1. So that's just a little bit of familiarity with the function. And if I go further with this, oops, it's not even correct. It's x squared minus 1 for the second one. They multiply to positive 1. For the last terms, the first term is multiplied to x to the 4th. Inside product and the outside product will combine to give us negative 2x squared. Okay, so then from there, the first part will factor as a difference of squares, x minus 1, x plus 1. The second factor is the same difference of squares. So as I look at this, x minus 1 is a double root, so I could say this is x minus 1 squared. And then x plus 1 is repeated, so that's a double root also. What that means to us for the graph is that x equals 1, we're going to have a double root. X equals negative 1, we're going to have a double root. So this is a double solution, x equals positive 1. This is the double solution, x equals negative 1. An easy point to find would be if I plug 0 in for x, I get a value of positive 1, so I know I have to go through that point. It's x to the 4th, so there's a maximum of 3 turning points. I know that the n behavior, because it's an even exponent, and the leading coefficient is positive, that it will be going up on the right, up on the left, has to bounce and hit that point, go through our y-intercept, bounce and hit that point. I see 1, 2, 3 turns, so it's hit the maximum number of turns. I used my bounce points that were these zeros or x-intercepts, and I have a pretty good idea of what this graph is going to look like then. All right, so can we write out a polynomial if we're given the zeros? So if x equals a is a 0, then we can factor it as x minus a. In this example here, if -2 is a solution, then x minus -2, which would be x plus 2, is a solution. Likewise, we have x minus this, x minus that binomial. So I'm going to multiply them all together, and you'll notice that these two look the most confusing, and they are conjugates of each other. And what you're going to see is if you have one radical like this, you will have its conjugate that will also always be a solution for us for these polynomials. To begin with, I'm going to multiply the two conjugates with each other and then get to the x plus 2 eventually. So x times x is x squared. X times -1 is negative x. X times positive root 3 is x root 3. Now, -1 times x is negative x. -1 times -1 is positive 1. -1 times positive root 3 would be negative root 3. One more time, negative root 3 times x is negative x root 3. Negative root 3 times -1 would be plus root 3. And then negative root 3 times positive root 3 would be negative 3. Combining all these terms, we are going to run into some opposites here. Positive and negative x root 3, positive and negative root 3, so those radicals got moved out. There's x squared, there's a negative x, and then another negative x, we have minus 2x. Combining those, and then 1 and a -3 makes -2. All right, so now we're going to do one more last multiplying. X is going to get distributed, x cubed minus 2x squared minus 2x. Then the 2 is going to distribute, plus 2x squared minus 4x minus 4. Combining our like terms, we're going to have x cubed, x squareds drop off, minus 6x minus 4. The last thing we're going to look at is the intermediate value theorem. So let's say that we have a polynomial and we're trying to find the zeros or the solutions, and we just need to narrow it down to what range the solutions are in. So here's our function. You can pause the video and enter this into your calculator, and we're going to use the table to figure out where this solution is going to be. I'll go ahead and click over to my graphing calculator. So here it is. I can look at the graph of it. And depending on your viewing window, you might see all three of these solutions, or maybe just the first two. If you expand your window further to the right, a bigger X max, you can see all three. But I'm looking at 1, 2, 3 solutions, which would make sense because it is an x to the third equation. All right, so going back to my calculator, I want to use the table. So I'll go to second graph, which is the table. And I can see, first of all, between 0 and 1, the y value changes from a negative to a positive. So one of my answers will be between 0 and 1. And then if I look down further, I go from a positive to negative in the range or in the domain between x equals 6 and 7. So I know that there's going to be 0 somewhere in that region. And if we scroll down a little bit further, we're looking for one more place where the y values are going to change signs from a negative back to a positive. There it is. There's our switch. So between 11 and 12, between an x value of 11 to 12, we're going to get another 0